Well, that's good. I mean, keeping yourself busy, I guess, is always good. Yeah. So, how are you guys? How are Z and Devansh doing? Oh, how are you guys doing?
Great.
Any news or?
Actually, I have a question.
Okay.
I was training the generative adversarial network for my deep learning homework, and I'm currently having a problem. And basically, I plot out the loss function. To loss throughout the epochs. It's basically the discriminator's loss is going down, but the generator's loss is just like remaining in a straight line. You know what's like the cause?
I don't know.
Okay.
Yeah.
It's kind of tricky to train this generator for the adversarial game.
Yeah, I mean, I don't know. Like, I've dealt with like the discriminator having trouble with like loss, and it's usually you're like hitting a local minima or a local. You're not hitting the global minima.
Right.
But
it seems like discriminator has learned something. The generator does not.
Right. Right. Is it what kind of data set are you using for it? Is it like a
it's like position. So that's like X and Y for joints.
Okay. Yeah, I don't know. I wouldn't know. Does anyone else know what the problem might be, or?
I don't know actually.
Okay.
Yeah.
So Z is in US now?
Right.
I hope everything is good.
Thanks. But are you in?
I'm in India.
Okay.
So I had plans for going to Harvard, but that's cancelled. So, yeah.
Devansh had a. Oh, go ahead.
I think he can explain on something like that.
Yeah. Devansh has a question, or he has a question. Yeah.
Not decreasing.
Maybe you can explain the thing again if he is listening.
I see. I do that.
Yeah. Learning is the most important hyperparameter.
Fine.
Okay. So when it's too large, the gradient descent never converges. Ah.
That's probably why. Because I tried like 1,000 bet size and learning rates like 10 to a negative 2. Probably that's, I don't know.
Yeah.
Never mind, that started me.
It's good. We got a little bit of hands-on discussion of a problem here. Yeah, regularization would be next.
Thanks.
I got an email from Jesse. He said, everyone faces a learning rate issue when they start. I remember tripping myself many times. Yeah, it's yeah, and so 0.01, 0.1, and 0.001 should be good learning rates to test. Okay.
Thank you very much.
Yeah. So Devansh is sending the link for this tutorial from FastAI. So I got an email from Jesse. May or may not be meeting with us this morning, joining in. So, and Stefan he was actually at the NeuroMatch. You know, some of you were here before, heard me talk about NeuroMatch. He was actually at the spin-off of that, which was BrainWeb, and he actually proposed his own project. So the project he presented or talked about several meetings ago on brain-machine interfaces that he's doing, brain-computer interfaces, and he's going to try to start an open source project on that. So that's we'll see how that goes. Well, maybe we'll have to check in with him. That sounds good. So today I'm glad everyone's doing okay at least. Today we have some papers maybe to go over. I have a couple of discussion points, and then I was going to talk about the CSV comp presentation. If Jesse doesn't join us, I'll just kind of give a recap because I'm recording the session. We'll be able to see afterwards. And then if you have anything else you want to add to the agenda, we can. Did any of you have anything else to add to the agenda? Or?
Yeah, so like you sent a mail about this paper that we might be submitting to. So how's that going?
Oh yeah, the paper. I submitted it to that MBDT journal. So it's a journal that takes, you host it on archive and it puts it in their format, and so it's it's a pretty decent journal. I don't know how, because of the way the paper is written, I don't think it would be suitable for the Journal of Open Source Software, which is one of the other ones I was thinking about. But I didn't get everyone else thought it was a great idea, so I don't know if I got your response, but yeah, you're all right with it. So yeah, it's been submitted, and I don't know, these days, people are dealing with a lot of issues, so I don't know how long it'll take, but it's submitted, so that's the important thing.
That's great. So once they give some confirmation or something like that, you can inform us.
Yeah, well, I think the way their review process works is that the editors have to approve or disapprove, and they get some feedback from a reviewer. It's a little bit different than some journals, and then it's accepted. But, it has to be something that they find interesting and that it, makes sense to them and everything. So it should, like I said, I don't know how long it'll take, but
Nice.
Yeah. So that's the link to the video, the tutorial. Okay, there it is. Oh, there's Stefan. Here he is.
Hi, Stefan.
Hello, Stefan. We were just talking about you, actually.
You mean my presentation for BrainWeb?
Yeah, the project that you want to start.
Oh yeah, I've started it, and I was actually really surprised by all the feedback that I got, because there were like 5 to 7 people who wanted to work, and they contacted me on different sources. Some wrote me an email, others just entered this MetaMost channel. But I was actually working more on T1FI project, where we kind of have tried to convert T2 to T1 images, and so my project was basically left like not that attended as I would wish.
Yeah. But you did get some feedback on it.
Yeah, sure. Yeah, totally. So people are really interested and really passionate about it. Just I think the main reason was, of course, that it's kind of really mathematically hard, and you have to be more or less, you have to know more or less about stuff in this machine learning area to even begin in it. And so that was probably the some kind of barrier for the most of the people. So I just told them to read an article first, one article on EEG data, and another article where they have tried basically the same idea, but on the fMRI data. And I didn't get any feedback from the people after I've sent them these two articles. So I suppose that was the main barrier.
Maybe, yeah, I don't know. I mean, usually, yeah, it's like people get they get intimidated or something. But yeah, no, it looked good. I was glad that you were able to get involved in that.
Oh yeah, thank you. Yeah, just it was out of the blue. We were just chatting in this room, and I thought of this brain web to be more like some, like you have it usually. So you have invited set of speakers, like we had in Brain Hack, for instance, right?
Yeah.
So you have 10 projects that are stated before, and kind of you just have these 10 pitches, and they are really restricted to these 10 persons who have registered themselves some month before or something. But in this case, I was really surprised by the fact that they actually said, all right, you can just go on and pitch if you want.
Yeah.
So I just did that, and yeah, that's how it came around.
Yeah, I wasn't sure on what how it was going to be set up either, but so I mean, there were probably about 10 projects total, and they have a space on the website where you link the GitHub repository to some links so that you can check it out. So the way they've set it up.
Oh
yeah. So it's a lot of projects.
It was actually really easy also to put your GitHub project on their website. You just had to add BrainWeb in the topics on your repo, and that was basically it. So you didn't have to fill out some forms. It was done automatically, which was also really cool. And I mean, just in general, I really enjoyed the idea of this hackathon, the projects that we had, and also how the people were, in general. I must say most of them were just friendly and also kind of witty. So it was just totally enjoyable working with them together for these 3 days.
Yeah, that's good. That's good. Yeah, a lot of the projects seem to be neuroimaging or some sort of neuroinformatics type thing. So, but I don't know how your project falls into that. I guess it's neuroinformatics.
Yeah, well, I would say it's also maybe it's the most there is about modeling. So we are not sure, of course, but we kind of want to try to pull this visual information, basically to convert the EEG information to the visual information based on pixels. So just recreate the image out of the EEG signal. And there's, of course, a really big concern, which is kind of theoretical, stating that maybe there's just not enough information in EEG signal just by the nature of it, by how much information in bits can it maximally encode in the given time frame to reconstruct the image that was seen by the subject.
Yeah.
So yeah, it's kind of also a scientific project if you think about it that way. We could just write some formulae and try to prove them, or reject them somehow, just with using mathematical formulations.
Yeah.
Maybe that's also something we would do someday.
Yeah, you're sort of having to deconvolute the signal and find components and sort of map them to some sort of the stimuli. Or there's a lot of transforming and processing of the data. I mean, that's at least my take.
Yeah.
Yeah.
Yeah, there are of course some more concerns like the noise that we have. Like this, it usually is. So there will be some information that will be just not useful because it's not right. And then again, yeah, even if we have enough information, like if we could theoretically have enough information in an EEG JAG like signal, and this EEG data that doesn't also necessarily mean that we can, or we have to look for a right artificial intelligence model to be able to represent this EEG data in visual format, so to say.
Yeah.
Yeah, so there's quite a lot to the project, sure.
Oh, good. Yeah. So I don't know if you have a link you can share on the project if people want to check it out.
Oh yeah, sure. I will.
Put it in the chat.
All right.
Yeah. And so.
And did you actually help out in some project? I was just curious.
Yeah, I mean, did I in one of the projects? No, I didn't. I didn't get involved in anything. I was actually going to present something, but I didn't. I wasn't prepared, and I still haven't gotten back around to it. So I just got busy, and
Oh yeah, I see. Yeah, I just saw you in a group chat, and I was really surprised.
Yeah,
like, I would say hello, but I guess
yeah,
wasn't the place.
I had come there from the NeuroMatch conference. Well, I had actually talked to these people. They were actually the people who inquired about the Brandenburg vehicles, and they had asked about yes, they do work on cortical folding, and they were asking about if you took a model of the cortex or cortical folding, and you applied it to the Brandenburg vehicles, which is a little bit. I mean, I was intrigued by the idea, but I don't. It was just kind of a conversation, and then they were at NeuroMatch, which was the other conference, and so I wanted to attend that. I thought there were some interesting projects, but I didn't know what to present for something. I might present. I think they're doing in another couple weeks. So there are people going to, are going to provide updates, and then people are going to maybe propose new projects. I might get involved then, but we'll see.
Oh yeah, sounds cool. And I guess I've seen these people who, on this brain connectivity or brain folding topic. Was it on Twitter, right?
Yeah, I think so.
Okay, yeah.
So.
Just also what I've noticed from this whole brain or neuroinformatics communities, that also really a lot of them are on Twitter somehow, and they're really active there. So I even created a profile there for this.
Yeah.
Which is not the case, for instance, in bioinformatics. I don't know, in bioinformatics we just have one single account for whole of our lab and try to post something there. But here in neuroinformatics it's much more personal, so to say.
Yeah, I think different communities have different ways of kind of communicating and getting ideas out there. So, yeah. So yeah, I'm glad that you're benefiting from some of the. I know a lot of this stuff has happened because of the quarantines and all that, but I think the upshot is that this was something that needed to happen anyways. Getting these communities of people, online from long distances away, and and of course now something about open source communities. If you need any, resources on that, that we have some here, in terms of how to organize meetings and how to run the, collaboration community. So.
Hmm. Yeah, sure. Our meetings have also been helpful here to understand how it could work, more or less.
Yeah.
Hmm.
Yeah. Well, yeah.
And by the way, I recall just seeing it today. I don't know whether you have sent it to me or maybe I've just seen it occasionally on Twitter. But there's also going to be some OBHM hackathon. Maybe so they've planned a real-time hackathon for the end of this June 2020. But like today, I've seen a link where you can kind of register yourself to help them out, and they want to do it online now.
Yeah. Yeah. Well, I mean that's good. Yeah, that'll help participation. So I don't know. They haven't made any more details available on that. I saw a little bit about it, but as we can make a if when we get the information, we can make it. I can send it out to the group. So if anyone's interested, OBHM is of course the organization that sponsored our Twitter conference that we did, and then they do human brain mapping is their acronym, but they're interested in sort of computational problems and neuroscience and modeling. So that might be something useful for people. We'll see if people want to check it out. You can. I'll send some more information later. Thanks, Stefan, for the update. And why don't we go on to the papers here?
Yeah, sure.
Yeah, I'll present my screen. And we have some pretty good papers this week. I have a couple. We have two papers and one topic that I'm going to cover over the next couple weeks here. So, the first paper is on something called Intuitional Math. And this is by a physicist. He's Swiss. And he's pretty well published in physics. Nicholas Gissin. And he's, in the last year or so, he's been writing these papers on sort of an alternate way to represent things mathematically. So, in this case, he's writing this is actually published in Nature Physics, but there's an archive paper. So he talks about sort of the background here. He talks about two different types of math, Platonistic and intuitive. And so Platonistic is the kind of math that we use for most theoretical physics, maybe for most theoretical things like theoretical neuroscience or networks or any other science that you can think of. And so his argument is that Platonistic mathematics is not suitable for certain problems. And he talks in this paper about representing time and how in physics you do have you can represent time, but there's so much more you can represent with what he calls intuitive mathematics. And so he kind of walks through a little bit. It may be over. I mean, it was kind of over my head a little bit. It may be a little. If you're not like studying physics as as your first area of research, it might be a little over your head. But he does get into some. I think it's actually pretty well written and accessible. So he gives a couple of examples of how you can represent time using both types of mathematics. So, although classical mechanics is usually illustrated with clocks and other cogwheels, almost all classical dynamical systems are of a very different nature. They are chaotic. Because of the hypersensitivity of initial conditions, the future of the typical classical system depends on far down the series of digits of the initial condition. So he kind of talks about how to model chaotic systems as opposed to something like a classical mechanics type model. I lost the paper, there it is. And kind of walks through this. Let's see. So it's a lot of, there's a lot of stuff in here about representation, and that's really where intuitionist mathematics can be useful. So in intuitionist mathematics, numbers are processes that develop in time. At each moment in time, there's only finite information. And then he talks about, so like, in sort of Platonistic mathematics, you have a number line, and the numbers are static, and then there's a relationship between the numbers. In intuitive mathematics, each number sort of evolves over time. And I was thinking when I read this paper the first time, it seems like this is something that in computer science people have kind of broached with data structures. Like there are certain data structures, like point processes, that allow you to sort of treat a single number as a process, and there are different, types of data structures that actually, do this, and it's mostly out of necessity and not of theoretical needs. But I mean, I made that connection, and I don't know if there's more to that than that. It's just something I thought of. But anyways, I think this is an interesting paper, especially in light of the FQXI essay. And, we submitted it, and then I found this couple papers that he's written like a week later. So I probably would have mentioned it in the essay had I known about it then, but it's not in there. But I think it's a good follow-up to that essay. And so it gives actually a table comparing indeterministic physics with intuitionistic mathematics. And so in one case, past, present, and future are not all given at once. In intuitionist mathematics, digits of real numbers are not all given at once. You have indeterminism versus numbers containing finite information. In one case, time passes, versus in intuitionist mathematics, numbers are processes. So this is like just a bunch of things that, comparisons between the two approaches. So I think it's an interesting take on sort of mathematical representations and how we assume physics has all the answers, but maybe it doesn't, at least the way it's practiced now. The second paper is this: hippocampal neurons represent events as transferable units of experience. This is a Nature Neuroscience paper. And the hippocampal neurons are interesting, not least of which because there are a lot of different, there's a very, defined structure in the hippocampus. In other words, there are different cells that do different things, and they're very well characterized computationally. But also that they're also involved in spatial cognition. They're involved in memory consolidation, and maybe some features that we don't really know about. So there are some very strong connections to function as well. And so this paper is about representing transferable units of experience. So the abstract is: the brain codes continuous spatial, temporal, and sensory changes in daily experience. Recent studies suggest that the brain also tracks experience as segmented subdivisions or events, but the neural basis for encoding events remains unclear. Harry designed a maze for mice composed of 4 materially indistinguishable lap events, and identified hippocampal CA1 neurons. CA1 is a region of the hippocampus whose activity are modulated not only by spatial location, but also by lap number. So what they're doing here is they're setting up an experiment with rodents, and they're setting up this sort of spatially distinct track, and they're taking laps around the track, and the animals are representing both spatial location and sort of the lap number. So they're repeating where they're going over time, and they were representing that as a lap number. So if you were running running around a running track for 10 laps, you think about it, you keep track of your lap in your head, but you also know kind of where you are in space. And so these event-specific rate remapping cells, so they propose that there's a new type of cell for this. Remain lap specific even when the maze length is unpredictably altered within trials. So that the lap number isn't linked necessarily to the length of the maze or your position in the maze. And then which suggests that the ESR cells treat lap events as fundamental units. The activity pattern of ESR cells is reused to represent lap events when the maze geometry is altered from square to circle. So they're altering the shape of the track, and they're looking at how these representations change. So they're actually, these ESR cells reuse the same representation for different mazes. So if it's square, if it's circle, they reuse it and modify it. They don't build a new representation de novo. And then this suggests that it helps transfer knowledge between experiences. So this is, and I know some of you who are interested in machine learning know about transfer learning, but this is actually, transfer learning comes from neuroscience, and it's, the traditional definition is that you take one set of experiences and you can apply those things to another domain. So, if I say like I learned how to drive a car, and I knew how to do that pretty well, and then I wanted to go fly a plane, there are probably some things that you can transfer from driving a car to flying a plane. You'll transfer some of that knowledge over, not all of it, of course, but some of it can be transferred. They also study transfer learning in when people use flight simulators. So they'll train people in flight simulators to fly real planes. And it wouldn't work unless you could transfer a lot of the knowledge you learn in the flight simulator to the actual plane when you're flying the plane. So transfer learning works in the real world, and they're observing that it works here at the more fundamental level of representations. So ESR activity, ESR are these cells, is separately manipulable from spatial activity. So, like I said, hippocampal units a lot of times encode different aspects of space. And there are different cells for this. So they have what they call place cells, which are cells that represent certain places in the environment. You have face cells, which represent faces of people. You have object representation. And then you have what they call grid cells, which are, they represent sort of the coordinate system of the space that you're in. So you build a coordinate system of that space, and that's what grid cells are for. So the place cells on the grid cell work has actually won a Nobel Prize. And this quite recently, in the last couple of years, where a Nobel Prize, and it was for, I think, place cells and grid cells. So that, they give the Nobel Prize to people for, a combination of discoveries. So this one was like place cells, which were discovered in the 70s, I believe, and grid cells, which were discovered in the 2000s. And they kind of linked those two things together in this system. And so this is, I guess they're proposing a new type of cell representation. And so this may constitute an independent hippocampal code. So they're proposing that there's an event code dedicated to organizing experience by events. So this is like the grid cells represent the sort of the spatial coordinate system. ESR cells they represent events. And it's interesting that, on the one hand, you want to be careful about proposing a certain type of, cell for representing a certain type of thing. So, some people are still skeptical about face processing neurons. I think if you read the literature, you'll run into the term grandmother neuron, and that just refers to the fact that you recognize your grandmother's face probably if you know your grandmother and you grew up with them, and it's a familiar face, and so we as humans can recognize familiar faces much more quickly than we can recognize just regular faces, like put a name to the face, that sort of thing. And so people are still a bit skeptical of how those actually work. They know that process happens in the literature. It's been demonstrated that face processing works like that. But ascribing it to a certain class of cells is a little bit trickier. And so there's still a bit of controversy on that. But so just to give you some background on that. And so this paper goes through their discovery here. They did this. I don't know if they have a picture of the experimental setup. This may be. Let's see if we can zoom in on it. Not sure. This doesn't really have a function for that, but so they give these episodic experiences as a series of discrete events. So they give these different, they present these images here as episodes. Here's the example of the maze. So this is the maze. This is the rodent here at the top, and they do these different laps. So they actually, I guess here they do one trial is 4 of these mazes. Well, actually, I don't know if it's 4 mazes. I think it's just one maze where they have them run around in the perimeter of this maze. And so it's a square. And so you can see they run it 4 times, and that's a single trial. And during that running the maze, they have this, they record the activity from the brain of the mice. They have a system where they look at different. So what they're doing here in this figure B and C is they create mice, and one of the reasons you use mice for this is because you can create like a knock-in gene, and they use this Cray-Lock system to knock in a gene and give it some fluorescence. So like when this gene is upregulated, there's a fluorescent element that allows them to visualize the activity. So it's actually, in this case, it's a calcium trace that they're looking at. So when the calcium is upregulated, which isn't a gene per se, but it's when there's calcium activity in that part of the brain, they image the brain and they can see the activity. And so then they have these calcium traces, which are actually related to the activity of these cells. And so this is the experiment here. They're recording the activity. They have this reporter system which gives them some fluorescent measure of activity in the cells in that area. This is CA1 in the hippocampus. So you can see there's this sort of fluorescence. This light green and the darker green is the background. And so they're able to get some information out of about what the brain is doing during these trials. And then they give a reward also. So there's some reinforcement learning involved in this as well. And so they're rewarding every lap experiment. That's what these little candies are. I don't know what the reward was, but they give a reward and they have it set up that way too. So they make a number of conclusions. One is that ESR activity is transferable between experiences. So this is something in transfer learning. You can transfer this between different types of experience, but you have this type of representation. It's flexible in that way. ESR tracks the relationship between events. So it tracks different aspects of different events, and transfer learning helps in sort of generalizing between events and there are different things in the events that the cells are able to represent as well. ESR activity and spatial activity are jointly but separately represented in the same cells. And so, again, now they're saying that there is a spatial representation in these cells, but some of them also have this ESR representation, this event-related representation. And so that makes sense because you're in the hippocampus and you do need spatial activity or spatial information for this. And then these figures are just variations on the first one. And then ESR tracks abstract relational features of events and could support transfer learning. ESR tracks discrete units of experience. And discrete event modulated activity occurs with the continuous non-spatial activity. So those two things occur concurrently. And again, you would think that, if you have continuous non-spatial activity, which is just kind of like the experience, the flow of things in the scene or whatever, those aren't necessarily spatial things, but they have to be integrated somehow with event modulated things. So, usually associate events with, maybe some sort of, memory of someone talking, or, you're watching a movie, where you were, but you also want to know what you were doing in that point. And so that's kind of what's going on in the brains there. And so all this is quite interesting. I think I made a pretty decent case for this. So check this paper out if you want, if it's interesting to you. Let me put the folder link in the chat before we move on to this other thing. So that's the drive, and it should be open. You should be able to access it. If not, send me a note and I can give you permissions. So the last thing I wanted to discuss really quickly this week, but I want to go over it in the next couple weeks, is this double descent origins. And so this is something that Jesse sent he wanted to present this paper, and I don't think he ever got around to it. But this is a paper that appeared in PNAS last year, and it's reconciling modern machine learning practice and the classical bias variance trade-off. And in this paper, they talk about a double, what they call a double descent curve. And so, we can talk about this again in weeks, subsequent weeks. But basically, what you have is this U-shaped curve where, in like a training scenario where you're training a model on data, this is a machine learning model, and you have this capacity of H and the risk. And so the risk is of underfitting or overfitting. So as you can see, there's a high risk of underfitting and a high risk of overfitting for both very low and very high capacities of H. And so this, of course, you want to find this minimal point, which is the lowest risk of under or overfitting for capacity of H. And capacity of H, I believe, is the model that they're talking about here. So they're talking about H. It's the predictor. So it goes in, they talk about it up here. The predictor H sub n is commonly chosen for some function class H. So it's the function class, and then the predictor is included in that. And so you have this function that's doing this, classification task perhaps, and then this is the minimal point. So this is sort of what they call the sweet spot of training risk, where it's minimized. But then they talk about this other aspect of it, which is where beyond this, for higher capacities of H, especially for models that are very high capacity, like deep learning perhaps, you have this, the risk of overfitting goes up, but then it actually falls as you add numbers of parameters to your model. So this is what they call the modern interpolating regime, and it goes down over this capacity. So for even greater capacities of H, it goes down. And so this is kind of an odd result. And this is something that they talk about in this paper. And so what that does is that sets up this, and again, we're using Twitter for this tweet that someone was interested in this topic. And they said, spend some time investigating history of double descent. As a function of model complexity, I haven't seen it described before 2017, which is, I think this paper was 2019, but they described it in 2017, I guess. As a function of sample size, it can be traced back to 1995. Earlier research seems less relevant. Also, I think we need a better term. And there's a whole thread on this. The term double descent was coined by Belkin, so that's the paper we just looked at. But the same phenomenon was also described in two earlier preprints, Spiegler 2019 and Advani and Sachs 2017. And so they have a number of results that they walk through in this post, or in this this thread, and it kind of gives some other experimental results that might be linked to this phenomenon. Let me see if this one is connected. I think it is. Okay, that's not the one I want. So there's some. I have a folder on this, and we'll kind of walk through this in the next couple weeks. I didn't want to talk about it too much this week, but I want to get into some of the stuff in subsequent weeks. And I'm hoping that Jesse maybe can join us in the next couple weeks, and we can have more of a discussion on this, since he was the one to bring this paper originally to my attention. There are a couple of papers here that are pretty accessible, I think. This one is Deep Double Descent, where bigger models and more data hurt. So this is a paper from ICLR in 2020, and this kind of talks about the problem, but this is kind of like a posterior discussion of it from the 2019 paper. So this is where they're kind of talking about this phenomenon. We show that a variety of modern deep learning tasks exhibit a double descent phenomenon. Whereas as we increase model size, performance first gets worse and then gets better. Moreover, we show that double descent occurs not just as a function of model size, but also as a function of the number of training epochs. We unify the above phenomena by defining a new complexity measure we call the effective model complexity, and conjecture a generalized double descent with respect to this measure. Furthermore, our notion of model complexity allows us to identify certain regimes where increasing or even quadrupling the number of training samples actually hurts test performance. So they walk through this, and this is related to, your data, it involves your training data, it involves your parameter, tuning your parameters, it involves the type of model that you use. So they're using this on ResNet 18, but it depends on your model, of course. If you use a different model, you're going to get a different result from this. And some models might be better than others in dealing with this problem. So this is the bias variance trade-off is usually what it comes up with in the literature. So they actually say in statistical learning theory, this goes back to Hastie in 2005. So there's a little bit different take on the history of this, but it basically says that conventional wisdom in classical statistics is that as we pass a certain threshold, larger models are worse. And of course, we know that modern neural networks, like deep learning networks, that's not really the case. That deeper networks tend to be better, but they also have a little bit more error, but they don't follow the same, they don't follow that dictum of larger models are worse. And so, indeed, conventional wisdom among practitioners is that larger models are better. And so they try to sort of resolve this contradiction. But finally, if there's one thing both classical statisticians and deep learning practitioners agree on, is that more data is also better, or more data is always better. So it's always about the data. And that paper is fairly accessible, I think, if you're into this area, of course. Another area or another paper is Beyond Overfitting and Beyond Silicon, the double descent curve. So this is a blog post. And so this kind of discusses, this actually goes back to like some physics luminaries, Freeman Dyson and von Neumann. And actually they mentioned the famous quote from von Neumann, with 4 parameters I can fit an elephant, and with 5 I can make him wiggle his trunk. And next week I'll kind of show you what that means. It's kind of interesting, given that you have these models with like billions of parameters. You know, that kind of stands in contrast to that result, where you're building these huge models of lots of parameters versus this statement. And of course, this statement was well before modern machine learning. So, but physics, they used to use a lot of parameters for things. The whole idea of modeling goes way back to, in statistical physics, where you have a lot of parameters and you have to make decisions about overfitting and underfitting, just like you do today. But, so they talk about this. This is the elephant this is just kind of drawing an elephant, and I can get into this next week. And so this is a little bit more accessible take on this. It's a blog post, so it's definitely going to be written at a higher level than this. So they talk about I guess this is their company that they have, and this is a company blog, so there's a little bit of propaganda in here for their company. So I would take that with a grain of salt, but it's definitely going to tell you something about the problem. So I think that's it for this week. And again, like I said, we'll revisit this in coming weeks. Finally, this is for Jesse, who might be watching this remotely. I wanted to discuss this presentation that we're doing for the CSV conference. And I think if you've been at the meeting the last couple times, you've heard us talking about this. So this is Epistemological Directories for Research, Development, and Education. So this is the presentation we're doing at this conference that's virtual now. And so this is the abstract was submitted. So we're combining some work that I've been doing on GitHub in terms of building educational infrastructure, and then Jesse's been building these what's he calling them? It's in here, frontier maps, and we're kind of combining those and talking about them to it's an audience of computer scientists and library scientists and other informatics people. So we're kind of walking through this outline, and we kind of set a date for today as being the day where we're going to complete the outline, but I think we can extend that. I just wanted to keep on top of this. So I have added a couple more slides in here. I think barriers to interdisciplinary research and education is a good beginning slide. We talked about origins in that this sort of approach has its origins in Web 1.0. We have an introduction to knowledge spaces. So this is my section, and I have to yet finish this, but I'm kind of walking through the knowledge spaces. I'm also connecting knowledge maps to knowledge spaces. So these are knowledge maps, and these are just like diagrams of different events that occur in different fields. Like this is a graphical history of machine learning, and this is a knowledge map of artificial life. So in artificial life, these events happened, and they have they're connected to a timeline where you can see them in serially as they've happened. And so it gives people an idea of what's been going on in the field. And then also talking about something called epistemological maps, which are ways of characterizing a field, what we know and what we don't know. And so then I talk a little bit about controlled vocabularies in history. So, controlled vocabularies are this idea that you can build a set of words that represent, a set of concepts, and that you use the same words. You have like a set of root words that people can use and not get confused by a topic or a term or a concept. And then we talk about like writing history. So, we want to have, on the one hand, we want to have standards. On the other hand, it's important that we don't monopolize the standards and exclude certain ideas. And so that's going to be, I think the people in this audience will like that. And then here's the frontier maps area. So this is where Jesse, wants to work on this area. I suggested we add something on the theoretical minimum, which was a book published several years ago. It basically includes everything you need to know to be sort of coherent in undergraduate physics. So, to start doing physics and sounding like you know what you're talking about, you have a number of topics in this book that are sort of the core of the curriculum. So we can talk about that, and then we can get into a little bit more on the frontier maps, a little bit of detail walking through the maps and how they're relevant to online learning. And then a cybernetic model of interdisciplinarity. So, how do we build a model of people using these things and, regulating knowledge and regulating, what they learn. And so that's what this slide is for. And I haven't really worked out the entire argument yet, but it's something we can talk about. And then finally, this is an advertisement for the Data Reuse Initiative, which is something I'm just going to advertise to people there, and they can, maybe they can join in. It's like a group like our group, except it's on a different topic, and we're trying to find people to collaborate on that. But I think this would be a good and final slide for the presentation. But there's a lot more work to do on this. So it's a 30-minute talk, so we need to kind of pick up on it a little bit and get it completed. And then I don't know if it's open. I think it's open to people to come by, but we can definitely supply a recording of the presentation for people in this group if they want to see it. So we're at the top of the hour. I just wanted to ask if there are any questions before we go. I know I promised that I would go over some of the stuff on the contextual geometric structures. I still have yet to work on putting that together. But I mean, I wanted Jesse to be here too for that. But so we'll talk about that in maybe next week. Mm-hmm. What I wanted to do is I had a bunch of conversations on Slack. I wanted to get together and put on a FAQ for this. So that should be coming, and we'll talk about that when it's up.
Mm-hmm. So still we have like time for the Google Summer of Code results. So we have time for the Google Summer of Code things and CGS things, so we can do that later.
Yeah.
Like in coming.
Yeah. I mean, yeah. So and for the community period for that, we're going to be doing that in these meetings as well. But the community period will be, I think, more along the lines of learning about kind of both open source and open science, and then also about that platform. So I wanted to give some, pretty good background on it during the community period, because it's something that you're going to be asking questions about. So we might as well just get a good primer to it out of the way. And then everyone else will learn about it as well. So that'll be in upcoming weeks. Okay. So if there are not any other questions, I guess we're at the top of the hour. So once again, thanks for showing up and being a part of the meeting. And I hope you all are doing well, staying healthy. If you need to take some time off, let me know. If there's something you want to do while you're in quarantine, let me know. Like I said, oh yeah, no problem. And we'll be revisiting the double descent stuff in subsequent weeks. I just wanted to kind of talk about it a little bit this week, and then next week we'll talk about it some more. And there's a lot of other stuff in that directory that I found on it, so we'll talk about it more. Yeah. Okay, guys. Talk to you later. Have a good week.
Bye, everyone.
Bye.
Thanks for the update. Have a good week.
Yeah, you're welcome. Bye.
Goodbye.